Hi, my name is Ali Shirsavar from Biricha Digital, and in this video we're going to explain the concept of gain margin and phase margin in order to assess the stability of a product such as a power supply. Imagine that you've got a product. For simplicity, let's just say it's a power supply. And imagine that it's completely stable on your bench. So you've tested everything and it's stable. What you don't want to happen is that you shipped this as a product and then it goes to the customer, and under a cold day, hot day, under whatever certain conditions, your product, your power supply goes unstable, because then you're going to have to go and service it, or maybe you have a product recall. So in addition to knowing that our power supply is stable in our lab under our condition, we always would like to know how far away from instability our product is. So we want to know how much margin we have before the thing may go unstable, in order to have some confidence that we can ship it without having any problems. And these we assess with typically gain margin and phase margin. For simplicity, let us say that we have a positive feedback system. I know we deal with negative feedback, but just to show instability, let us consider, just for simplicity of teaching, that we've got a positive feedback system. So that's plus, plus. Then let us say that I've got a proportional controller KP with a gain of 1, and then I've got a plant. Again, I don't really care, it's just for showing a stability. Let's say that's also got a gain of 1 across all frequencies, and my output is going out and is coming here. Okay? Let us say that I ask for 1, and again, for simplicity, let us say that the output is near 1. Right, approximately 1, let's say 0.9999, it doesn't matter. You can immediately see that this system is going to be unstable. And the reason is 1 plus 1 is 2, times 1 is 2, then it goes back, plus 1 is 3, 4, 5, and for a bounded input, you're getting a bounded output, and therefore it's unstable. So we can just say right now that if you've got a positive feedback with a gain of 1 or bigger, it's going to be unstable. Now, this does not happen if this gain here is less than 1. Let's say if that were a gain of a half, then what would happen is you get 1 plus 1 is 2, times a half, times a 1 is 1, and it goes around, and now you can see that the output does not get bigger and bigger and bigger. So let us define then for this condition, if you have a positive feedback with a gain of bigger than 1, we're definitely going to be unstable. That was the case of a positive feedback. We know in reality that we're dealing with a negative feedback system here, but what will happen is that this thing will increase the phase shift when you add a sine wave into it, to a point whereby it will invert. Let me explain. Let us say that I've got a compensator. Plant again stays at 1. We don't, for this particular example, don't care about the gain, but let us say that I have designed the compensator so that as my injected frequency goes up, there will be a phase loss. Let's say that from 1 Hertz to 5 kilohertz, there is no phase loss at all, right? There'll be 0 degrees of phase loss. And then from 5 kilohertz to 10 kilohertz, this starts adding a certain amount of phase loss, and at 10 kilohertz, let's just say I hit a phase of minus 180 degrees. Okay, now you can see that if I inject a sine wave of 10 kilohertz, by the time it comes out, it will be inverted. Even though it's a negative feedback system, I'm putting in a sine wave this way, and it's coming out that way. This is sine omega t, this one is minus sine omega t, minus minus gives me plus. Effectively at 10 kilohertz I suddenly have positive feedback. So then I need to go and have a look at the gain. If the gain is 1 or bigger, I already know that it's unstable. So how far it is below 1 is giving me the margin before I hit instability, and that is called the gain margin. Okay, so I've defined something called gain margin, which tells me how far away I am from instability in terms of how much my gain is below 1 when the phase hits minus 180, because I get that inversion, positive feedback because negative feedback. Let us say now that in addition to phase change, this compensator also changing the gain, which is of course what happens in real life. Let us say that it starts with a very high gain, and as the frequency goes up, the gain starts coming lower and lower and lower. And let us say, again for simplicity, that at 5 kilohertz, my gain becomes 1. That is 0 dB in logarithmic world. So a gain of 1, I need to make sure that at this point, 5 kilohertz, when my gain is 1, my phase is not inverted. I will go and have a look at my phase. If it's at minus 180 degrees and my gain is 1, then of course it's unstable. Effectively, it's the same definition. This has flipped in size. My gain is 1. I'm going to be unstable. So what I would like to know is how many degrees away from minus 180 degrees I am before the gain is 1, and that is my phase margin. So I look at the plot, a Bode plot. When the gain becomes 1, that is 0 dB, that's called my crossover frequency, and how far above minus 180 I am, it's my phase margin. One final thing, you may be thinking, I'm making a DC-DC power supply. Why do I care about a sine wave of 5 kilohertz or 10 kilohertz? There are many reasons, but one of them is, let's say if you give your power supply a unit step, this edge, this sharp edge, according to Fourier, will contain pretty much all the frequencies, a lot of higher frequencies. We have done other videos that shows this exactly, the harmonic content, and therefore the unit step that you give to your power supply will contain a frequency which may have a phase shift of minus 180. Okay, so let us show gain and phase margin on a real Bode plot. I have got my Bode analyzer suite here. The red trace is the gain plot, and the blue trace is the phase plot. So first I'm going to get the tool to show me the phase margin. There we go. I've got a phase margin of 50 degrees. That means I'm 50 degrees above minus 180 when negative feedback becomes positive feedback. And then let us quickly look at the gain margin also. And you can see that I have got 7 dBs of gain margin. Again, that means that I am 7 dBs smaller than 1 when my phase hits minus 180. I hope this has been an easier explanation of gain margin and phase margin that you read in a control theory textbook. I hope you enjoyed the video. We run regular power supply design workshops and regular EMC workshops in both North America and Europe. I hope you can join us in one of those.